sine x dx, right? You let u equal to x and dv equal to sine x. Let's make the problem a little bit harder. X cubed. Okay. So, since we learned about integration by parts, obviously this problem we're going to do integration by part. I see that I got two types of function, polynomial and a trig function. Okay, so do it. Make a table. Derivative one column, integral on the other column. I choose x cubed for derivative because I know that I keep taking the derivative of x cubed. I'm going to have a smaller and smaller degree of isotope. And integral of sine x, I do this because it's going to make a loop. Integral of sine is kind of cosine. Cosine is sine with plus or minus. Okay. So derivative of x cubed is 3x squared, 6x, 6, and then 0. Integral of sine is cosine x. I think negative because the derivative of cosine is negative sine. Yes. Okay. Integral of cosine is sine. So sine x with a negative. Integral of sine is negative cosine with now negative become positive cosine of x. Integral of cosine is sine x. Okay, keep in mind this we do integral. Okay, so integral of sine is negative cosine. Integral of negative cosine is negative sine. Integral of negative sine is cosine because the root of cosine is negative sine. Yeah. Integral of cosine is sine x. Okay. I stopped because I got a 0 right there. So one more time, I'm gonna put the sign plus. Minus, always start with plus and then keep alternating the sign. Plus, minus, and then plus. The last row, you put an integral in front. So, the answer is going to be x cubed. Put the arrows, make sure you all get it. And then go down, go down, go down, and this way. X cubed, negative x cubed, cosine x. I got a negative right here. Minus 3x squared, negative sine x, so minus with minus become plus sine x, and then plus 6x cosine x, and then minus 6 sine x, and then plus the integral of 0 times something. Integral of 0 is a constant. You have the answer. Okay. So this is extra. It's after book. Now let me move on. I'll show you a couple more examples. Okay. What about this one? Integral of ln of x dx. Well, I don't know the integral of ln of x. I know the derivative of ln of x is 1 over x, right? But integral, I don't. So, how do I do this? If you think of integration by part, we don't have much choice in here. If I let this is my u, is dx, is dv, and I'll let u equal to ln of x, and I'll let dv equal to dx. If u is ln of x, then du is 1 over x dx. The derivative of ln is 1 over x, okay? And dv is dx, then v is x, right? And the derivative of v is dv, the derivative of x is dx. So I can apply the integration by part technique in here. Integral of u dv is equal to u times v, so x ln of x. You can write ln of x times x, but it looks better. It looks better if you write x first and times ln of x. And then subtract the integral of v du. So this is u dv. You have to subtract what v du. Integral of v du is v is x and ln of x, 1 over x. I mean dx. Oh boy, this is very nice because x and 1 over x is just 1. So integral minus integral of 1 dx. And integral of 1 is just x. And this is x ln of x minus x plus c. You have the answer. Okay. So sometimes it's really simple. I'll just show you another example. Okay. Try another one. Integral e to the x sine x dx. See, this, usually whenever you guys see this type of problem, you should think of integration by parts, because we have two different types of function in here. Exponential function, time trig function, and usually for integration, this is almost impossible to integrate two different types of function in one integral. So we somehow try to simplify or separate those. And integration by parts, even though it's not a perfect tool, but a very good candidate to choose to take care of this problem. So you gotta choose something as u, something as dv, right? Both functions are good to choose at integral, but I would choose e at the integral, because and when I integrate e to the x, I still have e to the x back. So I'll think of what. Let u is equal to sine x, and dv is e to the x dx. You can choose the other way around. You can choose u equal to e to the x, and then dv is sine x dx. But I like this way better, because integral of e to the x always have e to the x. When you do integral of sine x, you're going to have what? Negative cosine, and integral of negative cosine, you come back to negative sine. So I don't want to mess up with the sign. I may make mistake on that. So this is safe. U equal to sine x, dv is e to the x dx. Then I got du is cosine x, and dv is e to the x, so v is still e to the x. So my integral now becomes what? U times v, e to the x, sine x, minus v du, right? This is u dv, so it's going to be v du, integral of e to the x, cosine x, dx. So, what do we have in here? We have an integral of e to the x and sine. You come up with, well, this thing is we don't have to worry about no integral. We come up with something minus integral e to the x cosine. It seems like we're not going anywhere, but watch me try integration by part one more time. See what you got. Okay. Try one more time. Last time I choose u equal to e to the x. U equal to sine, right? So this time I choose u equal to cosine of x, and dv is e to the x dx, with that part right here. Then I got du is derivative of cosine is negative sine x dx, and then v is still e to the x. Okay. So this integral right here gonna be u times v gonna be e to the x cosine of x minus the integral of v du. So minus got e to the x. I got another negative becomes positive, right? Sine x dx. You see what happened again? It get back to e to the x sine x. So this problem becomes what? Integral of e to the x sine x dx equal to e to the x sine x minus the whole thing right here. Subtract that integral is equal to this. And then I can distribute the negative sign into the two terms. I got subtract this, and then the negative distribute the second term becomes minus. Okay. And here comes the best part of this type of problem. Even though you still don't have the direct answer yet, but on the left hand side you got integral of e to the x dx, e to the x sine x. This one was subtract e to the x sine x, right? So let's add that integral on both sides. Add the integral of e to the x sine x dx in here. You add the integral of e to the x sine x dx in this side. So on the left hand side you have what? Twice of those integral. E to the x sine x dx. And on the right hand side, this minus with plus cancel out. You got what? E to the x sine x minus e to the x cosine x. Okay? So this is what you have so far. So all you have to do is you divide both sides by 2. You have the answer, and don't forget that the plus c at the end. Okay? Because we have a plus c anyway. So let me write in here. I'm running out of room, so let me just cheat a little. Divide both sides by 2, divide by 2, divided by 2, okay? And then don't forget, put a plus C again. So. Integral of e to the x sine x dx equal to e to the x sine x minus e to the x cosine x over 2, and then plus C. All right. Let me give you one more example, and we're going to call it a day. How about this one? Try one more example. You guys see that the idea is pretty straightforward, right? So it's all about your time spent on practicing, your experience, right? The more you practice, then the more experience you're going to gain, and then the better, the faster you will be. Okay. In here, I get to the right sub right away, right choice right away, because I've been practicing quite a while. But if you choose the wrong sub, that'd be okay. Then just go back and then sub again and choose another U sub, okay? And it takes time to learn, okay? Try another one. Okay. Integral. On this line we have boundary, okay? From 0 to 1, tangent inverse of x dx. Anyone know the derivative of tangent inverse? Tangent inverse of x, derivative is 1 over 1 plus x squared, I think derivative. But in here we don't calculate derivative. We want to find what? The integral, the antiderivative of tangent inverse. Okay? Just like the Allen problem before. Well, we don't have much choice in here. The only choice we have is let u equal to tangent inverse of x, and then dv is dx. So this is my u, and this is my dv, right? So my du is going to be 1 over 1 plus x squared. My v is x. Okay. So my integral from 0 to 1 tangent inverse of x dx is equal to, well, you can kind of forget the boundary for now. 0 to 1, you just do the integral, and then at the end you plug in the boundary and you do a subtraction, right? So what? U times v, so what? X times tangent inverse of x, okay? Of course, this one runs from 0 to 1. We have that. And then minus the integral, still from 0 to 1 again, that's what we have. V du, so what? X du, this is, I forgot to write dx, okay? X over 1 plus x squared and dx. Okay? So this one is what you plug in. X is 1, tangent inverse of 1. This is 1 times tangent inverse of 1. Subtract 0 times tangent inverse of 0. This is 0 already. Tangent inverse of 1, what angle make tangent equal to 1? The angle is pi over 4, so this is pi over 4, okay? And all you have to worry about is this integral right here, so this is pi over 4, I think. Okay, tangent inverse of 1 is pi over 4. Okay. This one right here, I can tell you that we're going to do a U sub, a regular sub right away. For this point, I'm talking about this integral. From 0 to 1, x over 1 plus x squared dx. Let u equal to 1 plus x squared. I'm not doing the integration by part anymore, okay? Just a regular sub. Then du is 2x dx. This is calc 1. So this problem becomes integral, okay, x. So x dx is 1/2 of du. So x dx is 1/2. This is u, so this is 1 over u, right? X dx is du with 1/2 in front. Now we have to change the boundary as well. X run from 0 to 1, x equal to 0, and u equal to 1, x equal to 1, and u equal to 2. So the integral from 1 to 2. This is 1/2 ln of u run from 1 to 2. This is 1/2 ln of 2 minus 1/2 ln of 1. ln of 1 is 0. So this is 0. Okay? So the answer is what? I got pi over 4 for the first part, and then subtract 1/2 ln of 2. That would be the answer. Okay? Okay, so let me summarize the whole section for you guys. The whole idea of section 7.1 is something called integration by parts. It's come from the derivative of the product rules, right? Take the derivative of the product, you go to the first time the second plus the second time the first, and it gives us a formula for integration by part. The idea is whenever you have integral that's kind of hard, you try to do u and v sub, bring it back to product of uv subtract a simpler integral, so you can calculate. Hopefully that works. Okay. If it doesn't work, of course we're gonna learn later on other method to solve. Depends on the nature and the type of problem. But in this section, we are focusing on the integration by part techniques, and it's pretty significant. All right, and then we have 2 parts, and you see some example. We have to do integration by parts a couple times, and I introduced you a method which is not in the book called the tabular method. You see a problem, this type of one. Integration by part, you have to do like 2, 3, 4 times. You create a table, it would work. And some other problem, even though integration by part won't give you the exact answer, but it gives you the same integration again, and you bring it to the other side, you simplify, you should have the answer. Okay? And in general, integration by parts technique seems to work a lot if you have a type of integral that have 2 different types of functions inside the integral, and the idea is try to separate them. Okay? I never say it's guaranteed it's going to work, but I claim that it seems to work many times in that way. If it doesn't work, as I say, you try another way. Okay, let me stop the clip today right here. Thank you for watching, everyone. And one more time, have any question, please feel free to ask. Have a great day.